Today we want to start looking at quadratic functions. We want to start looking at quadratic functions in many different ways. We want to look at the pattern that we'll see in the numbers, the graph and the symmetry. We want to look at the function and its zeros, and then we'll look at a popular application of quadratic functions. So let's start with the form of a quadratic function, or the forms of the quadratic function. So a quadratic function is what we get when the biggest thing we see is an x squared. So that's the general form. We have a function, say f of x is equal to a times x squared plus b times x plus c. So the defining characteristic is this is like a linear function, bx plus c, with an extra term with an x squared in it. So a, b, and c here are constants, and this is the standard form. There's another important form that we want to look at, and we want to look at it right next to this one, and that we can rewrite the standard form in a vertex form. So this is what we're going to call the vertex form. So the two forms communicate different sets of information, and they have different forms. Notice that the standard form has an x and an x squared term, and the vertex form, all the x and the x squared terms are tied up in these x minus h squared. That's often useful for us. But we're conveying the same information, just in a different form. We want to algebraically be able to switch back and forth between the two. That's something that's a nice pure algebra exercise. And then we want to understand where these forms are, what these functions look like, and what we can use these functions for, what kind of applications we can see in these, we can use these functions for. So let's start off by looking at the pattern in the numbers. Let's look at the very simplest of all quadratic functions. Let's let f of x equal just plain old x squared. And let's make a table of values for x and f of x. I want to plug in some negatives as well as some positives. A lot of times we've been starting our discussions of linear, when we were talking about our linear and exponential functions, we were using a lot of starting off at 0. But here I want to make sure we get some negatives and some positives. So let's just evaluate x squared at each of these x values. Negative 3 squared. Remember, when we asked for f of negative 3, in f of negative 3, the whole negative 3 is being squared. We don't just write negative 3 squared, we write the negative 3 in parentheses and square that. So it's a negative 3 times another negative 3, or positive 9. Want to make sure that we don't just jump into the calculator and type negative 3 squared without parentheses, because then the square is ignoring the negative part. We're not squaring the negative 3, we're squaring the 3. So make sure you square the negative as well. So following along, negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0. And then we're going to have a copy of the left side over here on the right side. 1 squared is 1, 2 squared is 4, and 3 squared is 9. This is because we're raising to an even exponent, and we know that even exponents do not respect negatives. Even exponents try to make all the negatives positives. And so we see that happening, despite the fact that I have the open 4 here on the right and the fantastic 4 here on the left. They're the same 4s, I just randomly write them in different styles. I'm not sure what makes me write one over the other. So if we start to look at the patterns, notice that from 9 to 4, we have a decrease of 5. And then from 4 to 1, we have a decrease of 3. And then from 1 to 0, we have a decrease of 1. So notice that we don't have a pattern of repeated addition. From 0 to 1, we have an increase of 1. We should not have expected a pattern of repeated addition because this x squared is not linear. And if we're going to have a linear, only linear functions have that pattern of repeated addition. So we're not looking at a pattern of repeated addition. And this makes sense because, like we said, the function is not linear. But if we look at how f is changing, if we look at the rate of change of f, that is a pattern of repeated addition. Because if we look at the next level, from -5 to -3, that's an increase of 2. From -3 to -1 is an increase of 2. From -1 to +1 is an increase of 2. From 1 to 3 is an increase of 2. And from 3 to 5 is another increase of 2. So f of x does not have a pattern of repeated addition, but how f is changing does have a pattern of repeated addition. So it's linear one level down. So how f of x is changing does have a pattern of repeated addition. So it's not linear on that first level of subtraction, it's linear on the second level of subtraction. So we could think of it as being linear on the second level of addition. The first row of addition, those are not the same, but if we keep subtracting one more down, then it is always the same. So the rate of change of the rate of change of f of x is linear. Oops, I put too many rates of change. The rate of change of f is linear. So here's f, that's not linear. Here's the rate of change of f, that is linear. I put too much rate of change. The rate of change of f is linear. F is not linear, but how f is changing is linear. Pattern with a pattern of repeated addition. Now, this is true even if we have a larger change in our function. So if I look at another function, let's call it capital F of x. I'm just going to take x squared and make it bigger. And we're going to look at the values that we see in capital F of x. So I want to evaluate this. I'm just going to take all the values that we had in the previous one and multiply them by 5. That's going to be the end result. So capital F of -3 will be 5 times a negative 3 squared. Order of operations suggests that we take the negative 3 and square it first because exponents go before multiplication. So it's going to be 5 times negative 3 squared, which is positive 9. And 9 times 5 is 45. So f of negative 3 is 45. F of negative 2 is just going to be 5 times what we had for x squared. So 5 times 4 is 20. 5 times 1 is 1. 5 times 0 is 0. 5 times 1 is 1. And we're just going to get a copy of the left over here on the right. 5 times 4 is 20 again, and 5 times 9 is, once again, 45. So f is not going to be linear. Makes sense because we're not looking at a linear function. This is not y equals mx plus b. It's an x squared. But if we look at the change from 45 to 20, we are subtracting 25. From 20 down to 1, we are subtracting 19. From 1 down to 0, we are subtracting, oops, not 1. I multiplied 1 times 5 and I got 1. That's not the multiplicative identity. There we go. So from 20 down to 5 is a decrease of 15. From 5 down to 0 is a decrease of 5. From 0 to 5, it's now increasing, so it's an increase of 5. From 5 to 20 is an increase of 15, and from 20 to 45 is an increase of 25. So the rate of the f is not linear because the rate of change of f is not constant. And so that means that f, capital F, is not linear. And we saw that in the form because it's an x squared and not an x. But if we look at the rate of change of the rate, if we look at the rate of change of f, capital F, that is constant. So from negative 25 to 15, that's an increase of 10. From negative 15 to negative 5 is an increase of 10. From negative 5 to positive 5 is an increase of 10. From 5 to 15 is an increase of 10. And from 15 to 25 is an increase of 10. So the rate of change of f of x, the rate of change of f of x is constant. So the rate of change of f of x is linear. So the rate of change of the rate of change of f is constant. Therefore, the rate of change of f is linear. F itself is not linear, but it has a linear rate of change. So here's the pattern that we're going to see in the numbers. It's not the first level of subtracting. 20 minus 45 is negative 25. 5 minus 20 is negative 15. That first level of subtraction is not going to be constant because the function isn't linear. But the second level of subtraction is going to be constant for a quadratic function. What this means is that we can start filling out a quadratic, we can start filling out a pattern if we know it's quadratic. So let's suppose that we are looking at a partially complete, and let's table, and let's practice following this pattern. So I'm just going to walk x along, say, doesn't really matter where we start. Let's go -2, then -1, and then 0, and then 1, and then 2, and then 3. And I ran out of table, so I guess I'll stop there. So let's suppose that at -2, q of -2 is equal to 20. And let's suppose that at the first step, we subtract 8. So the first thing that happens is we subtract 8. This is not enough to establish a quadratic pattern, just having 2 points. It's not enough information, unless we know something specific about one of the points that were given. But this is not enough information. Let's suppose that instead of from -8, the next amount that we subtract is -4. So 12 minus 4 is 8. Now what we can see is that we went from subtracting 8 to subtracting -4. The rate of change is not constant, but the rate of change of the rate of change should be constant. So from -8 to -4, we see that's an increase of 4. So moving forward, we should expect to see another increase of 4, because the rate of change of the rate of change of q of x should be constant. That's where the constant happens. So from -4, we increase this change by 4 to +0. And so nothing changes. Then the next change down here will be another +4, because that's where things are constant. So the next change from 1 to 2 is where we're going to see a +4. And so that'll put us at a 12. Then the next change down here will be 4 higher. So that's where we'll see +8, and we'll be back up at 20. So it's knowing that things are constant down here helps us figure out the rate of change, helps us figure out q. We know at this level, that rate of change is constant. So the level above it, we can figure out how much change is going on. So we use the bottom line to fill in changes, and then we use the changes to fill in q of x. So this is what we're looking for with a quadratic function in the numbers. This is a little bit harder to spot than with linear functions and exponential functions. With linear functions, we're just looking at this first line of subtraction, and if that's not constant, then we start dividing. 12 divided by 20, and then 8 divided by 12. But in this case, we'll get different values, so this is not going to be exponential. So that's the pattern of a quadratic function in the numbers. Anytime we take a quadratic function and start filling in values, this is the way that this is the pattern that will show up. The first line of subtraction is not going to be constant. but the first line of subtraction is going to be linear. So the second line of subtraction is going to be constant. Well, that's where the constant shows up. Here's one of the interesting things that shows up with quadratic functions. Notice that in the 3 examples we had so far, an extensive number of examples to be sure, we've had the numbers on the left and the numbers on the right. We got a mirror image of the numbers. So quadratic functions have a middle to them. And since quadratic functions have a middle where the left side is just a mirror of the right side, the graph of a quadratic function will have symmetry. Here's what the symmetry looks like in numbers. There's a middle, and then if we're the same distance away from the middle, we're at the same value. So let's talk about graphs of quadratic functions. So we saw the symmetry in the numbers. The left side is a mirror image of the right side. That's what we're talking about with symmetric. The left side is a mirror image of the right side. So to have this symmetry, that means quadratic functions have to have some kind of middle. So this also means there must be some middle to the quadratic functions. We saw the symmetry in the numbers in all the examples that we've had so far. So here we have 8 on 2 sides of some middle. We don't see where the middle is. We don't see where it bottoms out. But somewhere between 0 and 1 is the middle, because at 0 and at 1, we're at the same level. At -1 and 2, we're at the same level. At -2 and 3, we're at the same level with the 20. So there's the symmetry in the numbers. We'll also see the symmetry in the graphs. So the symmetry will appear in the numbers. And we also want to identify the symmetry in the graph. Let's take a look at the graph of x squared. And I'm going to use my favorite graphing calculator, Desmos. So let's take a look at, here's the graph of y equals x squared. And we can see it has this rounded V shape. Sometimes people say this is a U-shaped graph, and I disagree. A U is kind of vertical on the sides. Here the sides are going off at an angle, and the sides always get steeper, but they're always going off at some angle. They don't go vertical like in a U. So don't call it a U-shaped graph. Be sophisticated and call it a rounded V-shaped graph. Rounded because we have this rounded bottom rather than pointy bottom. But notice that if I pick a y value, let's say y is equal to 4, that those points, -2, 4, and 2, 4, are evenly spaced around the middle, which is at 0, 0. And here we have these two values at the same place. If I pick another value, say y is equal to 6, these intersections aren't going to be at nice points, but we got negative 2.449 and 6 and 2.449 and 6. So when we are 2.449 to the right and to the left of the middle, which is at 0, we have the same y value. That's the symmetry that we see in the graph. This is how we see the symmetry in the graph. We see that the right side is the same as the left side. Points that are the same distance away from the middle of the graph will be at the same y value. Now, if I move the graph from left to right, let's move the middle of the graph to, let's say, x. So notice that if I change the x to an x minus 3, the middle of the graph is now at 3, 0. And the 2 points where y is equal to 4 are at x equals 1 and x equals 5. Those are both still 2 units away from 3. If I change this 6 to y equals 1, so we don't get funky numbers, there's the middle at 3, where x is 3. Here's where we have the same y values, at 2 and 4. Those are both 1 unit away from the middle. Then I get these two intersections at 1 and 5. Those are both 2 units away from the middle. And if I throw in another one, I'm picking squares because they work out nicely. Here's the right side of the graph, and we can see it's just a mirror image of the left side of the graph. 0 and 6 are both 3 units away from the middle, which is at 3. And if I change this to x minus h squared, I can just slide this graph back and forth, and we can see whatever value I put in for h, whatever value I put in for h, I get points evenly spaced with the same y's. So the middle is at negative 2.7, y is 1 at negative 3.7 and negative 1.7, 1 unit away from the middle. 2 units of the way from the middle will be at negative 4.7 and negative 0.7, and that's where we get 4. And then 3 units away from the middle, that's negative 5.7 and positive 0.3. So that's how the symmetry works. Points that are the same distance to the left and to the right of the middle are going to have the same y value. Points the same distance horizontally from the middle will have the same y value. And so that's the symmetry that we'll see in the graph. And as we saw from that demonstration, if we look at y equals x minus h squared, then from this part of the graph, we can see that the middle, the horizontal middle, the x coordinate of the middle will be whatever we're subtracting from the x. When it was x minus 3, the middle was at 3. When it was x plus 2.7, the middle was at negative 2.7. Now we're not going to keep calling this the middle of the graph. when we're talking about the graph, we're going to refer to this point that's the middle as the vertex. So the vertex is either the lowest point or the highest point on the parabola, because we didn't look at an example of this. But the vertex will either be the lowest point on the parabola or the highest point on the parabola. And that will serve as the middle of the parabola, the horizontal middle of the parabola. So all we're doing is saying, well, instead of just calling it the middle, we're going to give that point a name since it's so important. We're going to call it the vertex. All right, the next step is to do just an exploration of vertex form and to see how, well, let's just write the vertex form. And see how changing the h that's in the square with the x changes the middle, and what the plus k does and what the a will do. All right, that's going to be it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.